So in this problem, what are we given is an array of integers, and the array of integers is sorted in ascending order. We are also given an integer target, and we need to write a function to search the target in the array of integer. And if that target integer exists in this array of integer, then we return the index, that is where we found our target. If the target doesn't exist, then we return a -1, and we need to solve it in O of log n time complexity. Now let's take this example and try to solve it. Alright, so we have this example here. Now let's just see how would you solve it using brute force solution. So to solve it using brute force solution, what we do is we have a value, and we need to check if the value exists in this nums array, which means that we are checking this value with the values of each of the elements in this array, right? So using brute force, what we would do is we would compare the value 9 with all the elements starting from 0th index. So we compare 9 with 1 and we didn't find the value, so we compare 9 with 0, 9 with 3, 5, and finally 9 with 9, and since we found our result, we return the index. So index would be 0, 1, 2, 3, and 4, right? So these would be O of n time complexity in worst case. But what we are asked in this problem is to solve it in O of log n time complexity. So how are we going to do that in O of log n? So for that, we are going to use binary search. So what actually is binary search? Let's look at that. So binary search is performed. First of all, for us to perform a binary search, the array should be sorted. So it should be sorted in ascending order. All right, so it should be sorted, and then all the elements in the sorted array should be unique. Okay, so it should be unique, and yeah, so these are the two criteria that we should be satisfied. And since we are already given that it's sorted in ascending order, and we are also given that all the elements are unique, right? It's written somewhere here. Yeah, so all the elements here are unique. So since we have since both these conditions are satisfied, we can use binary search in this solution, and binary search can solve this problem in O of log n. So what's binary search? Now let's look at the example and try to solve it. Let's try this example using binary search. So we need to search, suppose we need to look for a value equals to 1, right? So if we were using brute force, we would just compare the value 1 with the first element and we would find it, right? But what if we were looking for value 8? So we would compare it with each of the elements 1, 2, 3 until the last element, right? So the worst case would be O of n, the best case would be O of 1, right? And in binary search, both of these would be O of log n. So both of these would be in worst case O of log n, and if we were searching for the value 4, it would be O of 1 time complexity in best case. So now in how is it O of log n? All right, so let's look at that one. So in binary search, what we do is we divide our problem into pieces, bits and pieces. So since this is sorted, what we know is 1 is less than 2, right? 2 is less than 3, and so on. So what are we going to do is we'll check the middle element. So since there are even number of elements in this array, so what we do is we divide this array into 2 halves using the floor value. So this would divide the element into halves. One half will contain 3 elements, the other half will contain 4 elements. Now this element, the node, the index that we are dividing from, we would check the value of this in with our value, our target value. And since our target value is equals to 1, which doesn't match the value 4, right? 1 doesn't match the value 4, but we know one thing, and that is that 1 is less than 4. 1 is less than 4, and that would mean that 1 lies towards the right of this point, right? Towards the left. So what we do is we shift towards the left. Now only this becomes our searching search space. So our search space has reduced by half now, right? Now we look for this search space, we get the middle value here. So now we have this middle value, and then we compare this middle value with our target value, and we again know that our target value is less than the middle value, and since it is less, we know that the target value would lie towards the left of the middle value. So now our search space again decreases, and this becomes our search space. Now this becomes our middle value. Since we only have one element, that element itself becomes the middle value, and we compare it with our target value, and since it is equal, we get our result. So what's happening here is we are every time dividing our search space into half. So basically what were the search spaces here? The first search space was this whole array, the second search space was the half of the array, and the third search space was the half of the previous one, right? So it basically took us 3 steps to find our solution, right? And what's the size of this array? It's equals to 8. So what's log of 8? Log of 8. So basically log of 8 means we are taking the base 2. So log of base 2 8 is equals to 3. Hence we are able to solve this in just like 3 steps, right? So this is what binary search looks like. Now let's try to solve this problem using binary search. So now here we are looking for our target value 9, and we have number of elements equals to 6, right? Starting from index 0 to index 5. Index 0, 1, 2, 3, 4, and 5. So the middle value would be the floor value, that is equals to 2, right? When we divide 5 by 2, it's 2.5. We take the floor value, it's equals to 2. Now for 2, we check this value with 9. It's not equal, right? But we know that 9 is greater than 3. That means we have to check towards the left only, right? So now our search space is divided, so that we just check the left portion of the array from the middle point. Now our middle becomes equals to 9 here, because there are 3 elements, one towards this, one towards that, and the middle divides it, right? Now this middle value is equals to the target value, and then we return the value. So that is how we are going to solve the problem. So that was the intuition, the approach that we are going to solve. Right now, how are we actually going to code that approach? So what are we going to do is we need the middle value, right? So we take our left index and the right index, and to find the middle value, we divide our left plus right, the sum of these, by 2, and then take the floor value of this sum, this equation. We take the floor value of this equation, and then we find our middle value. Now once we have the middle value, if the target is greater than the value element at the middle value, Okay, if the target is greater, then we go towards the left, right? That is left shifts towards that is our right would be yeah, so our right would be mid -1, but here in this case, since the target is greater than the mid value, now this becomes our search space, right? So in this search space, now we move this left to this point, that is left becomes equals to our previous mid plus 1. Now our current mid would be again left plus right divided by 2, that would be equals to 4. And similarly we are going to do that with the right, and finally we would find our result. Now let's try to solve this problem and code it down. So we need the left index, I'm just going to use L, and R for the right index, and that would be equals to nums that length -1, and then we are going to iterate over the while loop until and unless left is less than equals to right. Why should left be less than equals to right? Because of course the left index should always be less than the right index, and we are checking until left is less than equals to right because there might be a condition where both the left and right overlap, and that is where the middle value is also equals to left and which is equals to the right value, and that is the result. So now we we compute our middle value, that would be equals to the floor value, okay, of both the sum of left plus right divided by 2, and then finally we check if nums at mid is equals to the target, then we return our index m, else if nums at index m is less than target, that would mean that our target lies towards the right of our midpoint, right? So left index would now change to mid plus 1, else that would mean that our target is less than the middle value, so now our right would shift to mid -1. And if in case we were not able to find our target, that would mean that our target doesn't lie inside our array, and then that is when we would return -1. Now let's run our code, and yeah, so all our test cases passed. Let's try to submit this. Great. So this is how we solve our binary search with O of log and time complexity, and the space complexity here is constant. Hope you liked my solution. Let me know in the comments down below. Thank you.